Hello and welcome back to Differential Equations. We are still in Chapter 7, and today we get to deal with integrals, derivatives, convolution, and a whole bunch of other stuff, which is going to complete the story of transformations, whether it's forward or inverse, which is backwards transformation, right? It can be used again in both, and this is where you're going to see that special inverse that I talked about. So this section has a little bit of both, and I can't I can't label these as convenience formulas or something like that because there are no other ways of doing these things. In some cases, they turn out to be convenience formulas, but in many other cases, it's the only way you can solve the problem. So it helps us work on this stuff. So think of a partial fraction decomposition. Think what it gives in the end, right? And understand that when you have the partial fraction decomposition, you're going to have minimum of those two terms that in the beginning are multiplied, and then you want to transform them using partial fraction decomposition into addition. So technically you're starting with, let's say, 1 over s minus 2, which is technically 1 over s times 1 over s minus 2, and you want to change that into a over s plus b over s minus 2 so that you can use inverse transform. Yeah, but what if we can just cut that out and do something right here, right? So not go into partial fraction decomposition, but see that is there anything that we can do when we have this stuff? And the interesting answer to that is obviously, well, hell yes, right? So this is in terms of s, right? So this is the frequency domain. So I can just call this situation, I can call it f of s times g of s, right? And I want to take the inverse Laplace of that to get whatever function is the solution. Let's just do solution in time domain, meaning you're going to get some function of t, multiple functions of t or whatever. So is there a way to deal with this? And this is where the convolution property of transform kicks in and defines it as inverse Laplace of multiplication of two functions in frequency domain, which is their Laplace transformed, right? Is going to be given as the convolution of these two functions. Now we still don't know, right, what the hell this means, right? That's what the lecture is about. But the interesting thing here is that if I have this and I know how to deal with this formula, then I don't have to do partial fraction decomposition. So this one kind of cuts in and deals with it right here. And in the eyes of the previous example, this means, right, so if I have that example from before, where my f of s was 1 over s and g of s was 1 over s minus 2, if I remember correctly. So the 1 over 1 over s, right, that was simply 1. So this would give us f of t is 1, and this would give us g of t is e to the 2t when you do those inverses. So using the Laplace transform, inverse Laplace transform here of 1 over s times 1 over s minus 2, again, we are avoiding the partial fraction decomposition, which is kind of easy for this, but whatever, is going to actually be convolution of 1 convolved with this. And we are still in that mode. What the hell is this, right? I have never heard of the operation of convolution. I've never seen the star, right, which is like literally you put these 4 lines intersecting, right? And now we need to figure out what is this equal to, and then we effectively bypassed the partial fraction decomposition, right? And we did this problem, solve this problem in a different way. Okay, so now it's time for us to define the convolution. And the convolution between two functions, now this is definition, so we are going to use f and g, but maybe it would be better if I used capital F and G, but whatever. So convolution is given as the integral 0 to t of f of tau, is just a dummy variable for t, because we have t over here as a limit, so we can't use f of t. And then g of t minus tau d tau. We could have literally used any other letter than tau. If you have a problem with tau, you can replace it, but all of the notation forever is tau, because tau is Greek letter t. So you are replacing t with Greek t. Anyway, this becomes your definition for convolution. Again, we're not deriving any of these things. This is a vanilla differential equations course. In the honors course, we talk about it more in depth. Over here, there's your formula, and it does this, right? So now, what is my 1 convolved with e to the 2t? Well, by the definition over here, it's going to be 0 to t of 1 times g of, that's going to be e to the 2t minus tau d tau. So all I need to do is to compute this integral. Now, luckily, this 1 times doesn't do anything, so we'll just ignore it. But then I have to integrate this part here. Now, integration for that would not be any problem, hopefully, because you use basic u sub from Calc 1, right? This is a Calc 1 integral. It does have tau in it, but e to the 2t minus 2 tau d tau. And your u sub over here is 2t minus 2 tau, and you are supposed to find du, which is negative 2 d tau. Again, when you take the derivative of 2t in respect to tau, 2t is a constant in respect to tau, so it just dies, and the derivative of negative 2 tau is negative 2, and then d tau. So I don't have negative 2, which is very easy to fix. There we go. So we fix that, and this becomes now negative 1/2 integral 0 to t, and this becomes just e to the u du, which is now very simple. Right? We have e to the u computed from 0 to t, but we have to, oh, I forgot to switch the limits of integration. Holy nightmare. Hold on, guys. This is terrible. When you change your variable to u, you have to change your limits from tau to u as well. And for that, you just use the basic formula up there. So your lower limit for u is going to be when you plug in 0 for tau, so that's going to be just 2t. So that's a 2t. And then u equals, when you plug in t, is going to be a 0. So there we go. It's going to be 0 there. Again, the first time around, you plugged in a 0 for tau. So that kills the whole term. That's the lower limit. And then the second pass, you plugged in the t for tau, and it became 2t minus 2t, which gave you 0. So now you can swap the limits and kill the negative. There we go, much better. And this becomes 1/2 of e to the 2t minus 1, which is 1/2 e to the 2t minus 1/2. So if you had to do convolution of those two, this is what you would get. Because again, e to the 0, right? E to the 0 is 1, and then 1 times 1/2 in front. So convolution is this integral that gives us multiplication of two functions in a frequency domain. So frequency domain is the one with s, right? One that you get from the Laplace transform. So two functions multiplied in a frequency domain give us this integral of functions in a time domain. And essentially what this does is it bypasses the partial fraction decomposition and then use of the, the use of inverse Laplace transform to solve the problem. So that takes care of that part. Now, again, the way you use this in a problem is you transform your problem and then you solve the algebraic equation, and then instead of using partial fractions and inverse Laplace, you use inverse Laplace on each one of each one of the terms, and then you do the convolution, right, of that. It's just a different way of approaching the problem. So let's take a look at convolution of. I'll give it two functions. So one more. What is inverse Laplace of, I don't know, literally anything, like 5 over, let's use a trig one, let's say, exponential plus 9, and then maybe exponential s plus 1. Doesn't really matter what we pick. I could have just picked something from homework, but it really doesn't matter. I mean, we're just working on this. Okay, so what do I have here? Well, unfortunately, I have these 5, and I need a 3 up there. Yeah, let's just fix that because I just don't want to drag extra constants through. The 5/3 constant that I would need would just be in front of the inverse Laplace transforms at all times, and then end up in front of the convolution integral. So it's just going to be annoying to drag it around. So I'm just going to change that 5 back into 3, and now I'm going to have the nice and easy. I don't have to drag the constants around. So inverse Laplace of, this becomes sine 3t times e to the negative t. So that's our life. When you do you split these into two fractions. The first fraction is this one, and the second fraction is that one. So that's your sine, and that's your e. So those are the basic specs. All right, so now we get the convolution going over here, which is sine 3t convolved with e to the negative t, and that is going to give me the integral 0 to t, and then you can pick any of these to be for your convolution. You can pick any one of them to be your first, any one of them to be your second, and then you go from there. So if I pick the sine of t to be the same, right, sine of 3t, then times e, and now this one is going to have, instead of t, is going to have t minus tau. So negative t minus tau, which we can fix. And now we get to solve this problem, and hopefully you're already dreading it, right? Because this is integration by parts with that trick, right? Let me just see what we get. Let me see. Over here we get times e to the tau minus t, actually, in this case, because the negative will distribute, so they would switch their spots. Oh, this is not 3t, this is 3 tau. Holy nightmare. I was like, that's easy if it's t, but it's tau. Guys, I messed up. So this is sine 3 tau. There we go, much better. Sine 3 tau, because the tau is now your main variable for this integral. Okay, so now we just need to grind through Calc 2 for this problem, which is pretty much, good luck. It is. I will write it in the form you remember it from Calc 2, where e is first, and then the trig function is second, and then you are setting up your u as e to the tau minus t, and your dv as sine 3 tau d tau, and then your du is going to be negative e to the tau minus t, and your v is going to be negative cosine 3 tau over 3. And then you use your trusty arrow to make your integration by parts formula easy. Just this ice pack is uneven. I didn't put on a flat surface last night, so it's all crooked. My tablet is constantly rocking here. It's very difficult to write. Maybe if I move it here. It didn't help. Hold on. Okay, it should be better. What do we have? We start with negative 1/3 e to the tau minus t times the cosine 3 tau from 0 to t, and then minus integral 0 to t, and then we have minus and minus will give us plus e to the tau minus t cosine. The tablet keeps rocking, so I can't write 3 tau, and then there is a third in front, and then d tau. So that's our first pass on integration by parts. We got our first part out, but now we need to deal with this one more time. So I have to set up another integration by parts, u equals e to the tau minus t, and dv this time is cosine 3 tau d tau. Your du is again negative e tau minus t, and your v this time is positive sine 3 tau over 3, and we put our trusty arrow right there. Don't forget to copy negative 1/3 e to the tau minus t cosine 3 tau from 0 to t, and add to that in the parentheses here the second integration by part. This is nested, right? So you have another 1/3 e to the tau minus t sine 3 tau. Minus and minus will give you a plus integral 0 to t of e to the tau minus t. There's a third in front, and then sine 3 tau d tau. Yeah, that fits. Distribute everything, and we are almost done, right? Negative 1/3 e to the tau minus 3 t cosine 3t minus 1/9 e to the tau minus t sine 3 tau, all of that 0 to t from the beginning to there. And then minus 1/9. This is where your grade dies usually, right here, because you forget to distribute this negative 1/3 to the positive 1/3 to get negative 1/9. Like you are able to do calculus, you are able to integrate, you're able to do everything, and then you just completely mess up on that one. Okay, so now that we have this, we realize that that term is exactly the same as this term, which means we can combine them on the right-hand side of the equation. So this is no longer equal situation. Now it's the original problem of 0 to tau e to the tau minus t sine 3 tau d tau plus 1/9 integral 0 to t e to the tau minus t sine 3 tau d tau is equal to this mess here. Now the 0 will kill some of these terms and the t would, but for now we get to write this negative 1/3 e to the tau minus t cosine 3 tau. I wrote cosine 3t, it's cosine 3 tau. Holy nightmare. This is terrible. It's 3 tau. Cosine 3 tau minus 1/9 e to the tau minus t sine 3 tau from 0 to t. Okay, on the right-hand side, you have 9 nines plus 1 9, that's 10/9 of 0 to t e to the tau minus t sine 3 tau d tau is equal to, and now on this side, we get to plug in t's and everything, right? So you get negative 1/3 e to the 0 cosine 3t, when you plug in, you're plugging in t for each tau, minus 1/9 e to the 0 sine 3t. Now you need to plug in 0, minus and minus make plus, and you get 1/3, maybe I should go here, 1/3 e, and now when you plug in 0 for tau, you get your negative t, and cosine of 0, minus and minus give you a plus, 1/9 e to the negative t, and then you have sine of 0, and that term dies. So 10/9, or 10/9 is going to move to the other side, so it's just the integral you are looking for, which is the convolution integral. You're probably by now going, no, I'm going to stick with my partial fraction decomposition because this is crazy. Well, yeah, this example is crazy, but the previous one was a joke. So you can use it on the previous one and solve it much faster than partial fraction decomposition, I hope. Okay, so e to the 0 is 1. We get negative, oh, I forgot to multiply 9/10. And then you get your negative 1/3 cosine 3t minus 1/9 sine 3t, and then plus 1/3 e to the negative t, and then cosine of 0 is 1, and the sine of 0 is 0 kills the whole term. So you can factor out 1/3 and cancel it with 9. So the answer is, finally, right? There we go. The answer is finally when you cancel 9 with the 3 and 3 and a 3, and you get a 3. You get 3 over 10. You can put your e term first because it's positive. And then you have your minus cosine 3t minus 1/3 sine 3t. And that is the inverse Laplace. So inverse Laplace of whatever the hell we had here, it was something like 3 over sine squared plus 9, and then was s plus 1, I think, because it was e to the negative 1, right? E to the negative 1. Yep. Is actually equal to 3 over 10 e to the negative t minus cosine 3t minus 1/3 sine 3t. And yeah, go ahead and do your separation of no separation of variables. Your partial fraction decomposition, right? Do the partial fraction decomposition, and you have to come up with the same answer. So that's the convolution, and as I said, it's supposed to help. So you know that there is a job for a framing hammer, and there is a job for a little hammer, and there is a job for a sledgehammer, and we talked about it in class. Well, this is a very specific sledgehammer, which you use to break the concrete slab, and you definitely not use it to put the picture right on the wall where you can probably even push with your fingers into drywall without the hammer in the first place. But the idea is, have a right tool for a job. I understand that your exam, because you are still learning, and exam is literally, 2 weeks from now, because this is on the final. Yeah, exam is going to say, find the convolution, and then you just mindlessly can go in and just grind through actually Calc 1, or in Calc 2. I mean, we haven't done any differential equations here. It's just, here's the formula and grind Calc 1 or Calc 2, right? Use sub or by parts. This skill is actually important later when you are solving problems in thermodynamics or chemistry or whatever, right? 400 level courses, and you go, oh, I can use convolution and actually solve the problem faster than, sitting with partial fraction decomposition, figuring things out. So it's like a, sledgehammer, technically. Now, what else is in here? Well, the rest of the formulas are, that stuff that I refer to as convenience formulas, and the formulas that speed up the process a lot. And some of these formulas are insanely good because they cut out a lot of your work. So the cool one is this differentiation of transforms. Okay, pen. Let's see. Differentiation of transforms. And it does have conditions that the piecewise continuous function and all of that stuff. Laplace transform of negative t times f of t is equal to f prime of s. Holy nightmare, right? Because that means that the inverse Laplace of f of s is simply negative 1 over t inverse Laplace of f prime of s. And again, this is what we are after. Because forward transform, yeah, just use the chart or use the basic integration by parts and you're there. Like, no one stresses over forward transform. That's silly. You just do it. All right? But the inverse is the one that it's annoying and takes time and you have to bleed over it. So any formula that helps you with the inverse Laplace is really, really good. So what we can do now is we can pick a problem, right, and do the inverse Laplace transform having this in mind. Now, this is the derivative in respect to s. And you know what kind of formulas you get there, right? Simple polynomials, simple rational functions. You can deal with product rules, quotient rule, like in one simple move. Let's see if I can find something in the homework that would. Okay, so let's find the inverse transform. Problem 24 is looking for, they give you f of s as ln of s squared plus 1 divided by s squared plus 4. And immediately you go, what the hell, right? Because, yeah, what the hell? you have this ln here, right? And your equations earlier did not have ln when you were trying to do this. So you can't do partial fraction decomposition here because of ln. Okay, but what if I can differentiate this, right? So instead of writing inverse Laplace of f of s, which is inverse Laplace of ln of s squared plus 1 over s squared plus 4, instead of doing that, how about I just do negative 1 over t times the inverse Laplace of the derivative of ln s squared plus 1 s squared plus 4. Because maybe that's going to be easier. And actually, this is going to make it possible. Because what I have here is the derivative of ln, and that will kill ln. ln is gone, and then I can actually do my inverse Laplace, because there will be no ln. Now, there is an easy way to take this derivative, and then there is the hard way to take this derivative. And that obviously depends on your knowledge of pre-calculus and logs and stuff like that. Because you can rewrite this problem into ln of s squared plus 1 minus ln of s squared plus 4. Right? So this is something that, right, immediately, kills the chain, the quotient rule and all of these kind of things. Now, again, if you don't know it, you have to grind through the long process. But now, what I have here is ln of the first one. That's, you write the function downstairs and you put its derivative on top, minus, again, this is s, so be careful that it's not a 5 or something. And you have s squared plus 4, put its derivative at 2s on top as well. There we go. Oh, right? Well, these are our basic, right? Aren't these our basic Laplace guys, and they're already separated by minus sign, right? These are your cosines because they have s over s squared plus something squared. So negative 1 over t, and then you have open parenthesis 2 cosine t minus 2 cosine 2t, right? Because it's this 4 is 2 squared. So these 2's are the 2's that are in front, and this are your basic cosines that live in the chart. So we're good there. And you can factor out 2, make this a little bit nicer, but technically that's what it is. And we have now our right f of t, which is the frequency domain. Sorry, the time domain. So we couldn't even do this problem with partial fractions or anything like that because of the ln. But once the ln is gone, right, it introduces the derivative, and we can go from there. So it's a really good formula. In some cases, it's a convenience formula. In this particular problem, it was a necessity, right? Because there was no way partial fraction decomposition or something because you had ln in original problem. So that was problem 24 on your homework, and it's they have also inverse tangent, which is cool, and 4 problems that ln. One is inverse tangent, and one is kind of something like that. Now let's see. I would like to find another example. After this we have one more formula for integrals, and then we're done. So let's take a look at one differential equation that actually does have right where we would get a solution. So it doesn't matter which one we pick, like 30 for instance, it doesn't really matter. Tx double prime plus 3t minus 1 x prime plus 3x equal to 0 and x of 0 is equal to x prime of 0 equals 0. Remember, we can never do Laplace without this because derivatives have that in their thing. Okay. So now we are supposed to transform this and see what we get. All right. So what do I have? The formula that we know from before, like the Laplace of x prime of t, right, is s times, well, I used x here, so capital X, I guess. We use this with f. Let's put it the way we're used to. F of t, and then f of s minus f of 0. Now you know your f's are x's in this case. And then you have your Laplace for, this is Laplace of the first derivative. Now Laplace of the second derivative was s squared f of s minus f So s squared f of s minus f of, no, s, come on, s f of 0 minus f of f prime of 0. So this was our second derivative thing, but again, both of these are zeros because of that one right there. So we don't have to worry about any one of those, right? What we are worrying about are these things, and these are the things we never had before. So we have to be careful about that. This one over here is 3f of s. We know that from right, and this one is 0. So that's the easy part. Okay, so what are we going to have in this case? So we have the multiply by t. So it's this term and this term. We also have our derivative formula, which we just talked about, and that formula says that Laplace transform, I don't even know which color to use anymore, too many formulas. Laplace transform of negative t times f of t is going to give us f prime of s. So t times x double prime up there, right, has to be t times this one. So that's going to be the derivative in respect to s of s squared f of s, and then the rest of the terms are 0, so we don't have to worry about those. Good. Because we just have one t and then the negative. So guys, this negative is that negative. The t was in the formula, so I don't have to write it. And then just f of t is all of this, but then I don't have the other two terms because zeros killed it. Okay, so that's the first one. Good. Then I have plus, oh, I didn't separate this so you guys can see. This guy is 3tx prime minus x prime, right? So this first part will have the derivative and the second one will not. So, so we have this as plus 3, and then t is there. This needs to be a negative now. And then we have just s f of s, which is from here. And then we have minus x, which is the vanilla one of these. So that's just minus s f of s. And then plus 3 f of s equals 0. So this conversion, right, as you can see, it's possible. It's a little bit annoying, but it's possible. And we converted the whole thing into our system. Oh, oops. The derivative over here. Holy nightmare. So there's the minus from the formula. The 3 is the constant from the problem. S, so there is a t, which is given up there, which takes care of the t. And then f of t is s f of s. Okay, good. Now I need to differentiate the first term. What would that be? I have negative, and now I have a product rule. Copy the first, derivative of the second, plus copy the second, derivative of the first, minus 3s f prime s minus s f of s plus 3. Like, none of these are like terms because one has s, one has constant, one is derivative, so they're all different terms. So now I have negative s squared f prime of s minus 2s f of s minus 3s f prime of s minus s f of s plus 3 f of s equals 0. Now you can immediately see that you can factor out f of s. The thing that I don't like here is that I don't have any non-fs terms. So factor out f prime of s, get negative s squared minus 3s, plus factor out f of s. Oh, there it is. Okay, good. Now we're good. We're good. I panicked too early. When I do this, I get negative 2s from this term, I get a negative s from this term, and I get plus 3 equal to 0. Okay. So this becomes negative s squared plus 3s f prime of s plus, and this becomes negative 3s plus 3 f of s equals 0. Move this term to the other side, becomes positive. So now we have negative 3s plus 3 times f of s is equal to s squared plus 3s f prime of s. And move f of s to the other side, and you get your separable differential equation, right? This goes this way, this goes that way. So what you have is negative 3s plus 3 divided by s squared plus 3s is equal to f prime of s over f of s. So yeah, that problem was a little bit crazy, but you have now a separable equation over here that you can solve, right? You integrate both sides and you come up with whatever the answer is. So when you integrate here, this is definitely easy, right? Because this is ln of f of s. That's the basic idea right there. That's the cheap part. And obviously integrating this one ds over here is going to be a problem because you have to go and do partial fraction decomposition again, which is, yeah, but such is life over here. You have your negative 3s plus 3 divided by s plus 3, and that breaks into a over s plus b over s plus 3, and then I think you are picking up in my voice that I really don't want to do it, but I'm still doing it. AS plus 3A plus BS is equal to negative 3S plus 3. So your A plus B is equal to negative 3, and your 3A is equal to 3. So A is 1, and B is negative 4. So you have your 1 over S minus 4 over S plus 3 is equal to ln of f of S. And now you're supposed to do the inverse Laplace. Now this is where the inverse Laplace formula kicks in. Remember, supposed to kill ln, right? So it will be negative 1 over t times the derivative of f prime of S, and on the other side you have your 1 minus 4e to the negative 3t. Multiply both sides by negative t, becomes 4te to the negative 3t minus t equals to, oh, wait. I do this backwards now. Yeah, I know, ln is good. Let me just real quick stare this down. It's way too many of these things to flip around. So Laplace transform of inverse Laplace Oh man, I confused myself. I can't even imagine where you are at this point. All of this is good up to this line, so everything is certified up to here. It's this part here that it's messing me right up right now, to the point where my head hurts. The formula for inverse Laplace is inverse Laplace of f of S is equal to negative 1 over t inverse Laplace of f prime. Oh. Okay. Hold on. Hold your horses. Yeah, good luck with this. So e both sides, and f of S is equal to e to the 1 over S minus 4 over S plus 3. There we go. That's the one. Okay, so now, right, that's how you kill ln. And now you have f of S free, and that's what you needed, to have it free so you can do inverse Laplace. But before you do inverse Laplace, leave some space to stick that in later. This is e1 over S divided by e to the 4 over S plus 3. And now you get to stick inverse Laplace here. And when you do that, your left-hand side becomes f of t. So you win there. Now the right-hand side is the transformation, because now again you have the division of these things and then it's all terrible, right? So your job is to hopefully try and make it somewhat easier. And I'm wondering if the previous if I take derivative of that, yeah, but I can't do inverse Laplace anyway. So this is negative 1 over t inverse Laplace of the derivative of these. And this is why I think that it's actually better if I have only one e, because the derivative there would be itself times the derivatives of the things on top. Yeah, so I'm just going to leave it there. I'm not sure exactly now. I can't remember how to break this, because either case will not give me. Just trying to think of like 5,000 things at the same time. Okay, let's go and cheat and look at the. Oh, there it is, the delta function and the u function. Okay, good. Yeah, the solution for this is. Why is this problem here if the solution of this is in actually 7.6? So yeah, 7.6. I'm just gonna put like that. So that's where the solution is. But we got it. So let's review. I need this stuff. Especially it's written ugly in 2 lines. So you see that this differential equation you have is not constant coefficients, right? You see that. It has a function t and it has 3t minus 1 in front. So it's not constant coefficients, and you have to use this witchcraft, right, to transform it. Now, this transformation here is the one that we are using to transform, because you can use this as a forward or a backward transform, right? You just put inverse Laplace, it will cancel Laplace in front, and you have the inverse Laplace transform. So it goes both ways. And these are the old transformations that you guys had for first and a second derivative, which you still need. Now, our problem was nice and easy because we had all the conditions equal to 0, so all of these terms dropped. That doesn't happen all the time, right? Because you might have initial velocity. Like distance can be, right, start from rest and blah, blah, blah. That's, in physics, when you read the problem, it says the object starts at rest, right? Which means that your x is 0 and x prime is 0 because it starts at rest, right? Has no velocity to it, and it's at the origin, let's say, or it's at 0 displacement. So that's immediately that condition when something starts at rest. But that something could be already moving, right? And then you start measuring, so your x is 0, but x prime is, I don't know, 30 miles per hour. So in that case, x prime is 30. So you're not guaranteed always to have these 2 0 out on you, which makes arithmetic harder. It doesn't make problem impossible or something. It just makes your arithmetic more annoying to solve as you go down the line. So we do the conversion. Again, you have the formula, and look, you want to transform the second derivative over here. I think, let me just go in a book and see. There it is. Higher order derivatives. So this can help you. Laplace of Tn of f of t. So when you have t squared and so on, is going to be negative. I don't want to forget this one. the nth derivative of S. So if you have t squared in front of your, right, if you have t squared in front of your term, then you can take two derivatives of the original function for your transformation. So you have f double prime, in which case you are actually hoping to transform your problem into constant coefficient problem rather than what we had, separation of variables problem. So for the basic equations, first order and the constant coefficients, the Laplace transform transforms the equation into algebraic equation. You can solve and do inverse Laplace. But if you have a non-constant coefficient equation, and then you have, let's say, t squared and all that kind of stuff, that can create higher order differential equation to be solved inside the frequency domain. And obviously that brings, right, more work. What you definitely don't want to get is the undetermined coefficients inside the frequency domain, which, yeah, you can double up on Laplace and then undo two Laplaces. I mean, it's it's fun. I don't know. It was fun for me to learn all of these things because it's like, it's like a puzzle, and you go step by step and you practice enough to kind of unpackage all of these and apply all of the formulas and all of that. So that's what we have for derivatives. And there is your integration of the transform, which is also something that could be very useful in our calculations. So integration of transforms Laplace of f of t divided by t. I mean, this should be common sense immediately because you had times t for derivatives, so for integrals it better be over t. They use sigma for the notation. I just checked the book. You could have used tau. It's not a problem. Your answer will be in terms of s though, so whatever. And this gives us that our inverse Laplace, which is what we are after most of the time, of f of s, is going to be t times inverse Laplace of the integral s to infinity of f of sigma d sigma. Guys, this is just the same formula you get. So the formula we need and use right here is a simple algebraic manipulation of the top formula, because if I put inverse Laplace on both sides, you see that these Laplaces cancel, and then I just multiply both sides by t, which would cancel the t, and you have the t in front because I multiplied both sides by t, and you get this formula. So remembering just the top one and dividing. Now you might be saying, why would I do that? Because I'm going to have, reference. I understand you're going to have reference for the exam that it's coming up, because you can cheat that way, no one can catch you, right? Because you're doing the exam, right, in a room, no one sees you. But try to pull that off on your thermodynamics exam when you have to use this stuff. And there will be no reference because you'll be doing it 2 years from now in the classroom, right, where this nonsense is over with. So there you go. So remembering the top formula and simply applying inverse on both sides and multiplying by t on both sides gives you the formula for inverse Laplace that you want to use. And from this point on, you can, go and use that one as well. It's used the same as the previous one. You just go through the calculation, and then instead of dividing by negative t, now you're multiplying by t, and you're integrating your f. So I'm just looking for an example somewhere for the integral transform. Well, actually, why don't we take a look at just a forward transform. Oops. Forward transform of t sine 3t. This is your problem 15. Now, you're going to say, oh, but that's the basic one. It's in the chart. Yes, it is. If you look in the chart and you go on the front cover, I'm staring at it right now. It used to be somewhere over here. There is e times sine. This one times sine. The hell is the t times sine? Maybe I pulled it off the internet. Oh, probably it's in the other book. This is... Oh, this is Penny Edwards Penny. Okay, maybe in the other book. I don't have it here. Probably the boys' book has it. I know I've seen this in a chart, right? Some charts will include it. So yeah, that's one way to do it, right? The other way is to actually go in and do that terrible, horrible actual transformation integral, right? Where you have to work out everything, right? 0 to infinity e to the negative st times t sine 3t dt, right? Good luck, it's going to take a year. Now, what you can do instead is just the top up there, because Laplace of f divided by t, right? So Laplace of f divided by t is going to be, so now remember, that's going to be Laplace of t sine 3t over t is going to be, see these guys cancel, is going to be the integral of, so now that t, right, is gone, and all I have is the integral 0 to, s to infinity of the Laplace transform. Now Laplace transform of sine 3t. Now that's a basic one that we know, right? Sine 3t is just 3 over s squared plus 9. But it's not s, it's now sigma d sigma. And you just solve this integral instead. Now this integral is the basic inverse tangent integral. So that's inverse tangent of 3 sigma from s to infinity. And wait, that's unbounded. No, it's not. What the hell am I talking about? This is inverse tangent. I'm completely losing my mind today. This is inverse tangent. So this is limit as b goes to infinity. Holy nightmare. Tangent minus 1 of 3 sigma s to b. And inverse tangent has the, there we go, horizontal asymptote, it's pi over 2 as the limit goes to infinity. So this is pi over 2 minus tangent inverse of 3s. There you go. Now, if you flip the book back to homework, I'm just going to write here in parentheses, if you are looking through your notes at all, look at problem 26. It will have inverse tangent in it. So now you know what that's going to go back into. And you also understand why something like this would be included in a chart, because, right, going back and forth is between t sine t and inverse tangent. So it is something that you could easily include in the formulas. I think that the other book actually has it, because I remember that I've seen it in one of the charts. It's probably the other book that we are not using for a couple of years now, but it's there. So huge convenience, right? Just imagine this triple product over here, right? Because you have 1, 2, 3 functions. So you technically have a nested product in there, meaning product within a product, meaning integration by parts upon integration by parts upon integration by parts, and how many you need, right, to solve the problem. Because your first integration by parts is going to be between E and the rest. But when you need to integrate the rest, that's going to be integration by parts to kill that T. And then the entire problem is E times sine, which is the whole long procedure of E times sine. So this is minimum 4 integration by parts if you want to do it by regular means. If you don't have the chart with this available, and your textbook doesn't, right? The old one probably did, or maybe I've seen it somewhere else. I don't know. Maybe it was online resource for all of these things. I don't remember. I just know I've seen it somewhere. So, you know, this integral formula helps us. Now, we did do the forward transform, meaning going from T domain into, so that's not the blue one. It's the one above that we used. Blue one is inverse Laplace, which is used the same way. I mean, you multiply by T and then you integrate and you're done. So hopefully you will spend a couple of hours enjoying that and practicing it. So yeah. All right, so we're going to take a short break now because we still need to take a look at least a little bit at 7.5 and then end our chapter 7 so that we can dive into chapter 8. We only have 2 sections in chapter 8, but they're very interesting if you catch my drift, right? So I'll see you back in about 5 minutes or so.